Hello everyone, good afternoon. My name is Abhishek and welcome to AutoGrad Era. So in this video, which is the second video in this PyTorch series tutorial, we're going to learn about tensors. So tensors are the building blocks of PyTorch. Like everything we do in PyTorch happens on top of tensors. So even when you load an image in PyTorch, it is represented as a tensor, and like any data type can be represented as tensors. Tensors can contain integers, floats, and whatnot. So in this video, we're going to study tensors in detail, and we're going to see how we can use tensors to perform different operations, and we're going to see what functions are present in PyTorch which can be applied on these tensors, right? Summation, getting averages, means, and like standard deviations, and all those kind of stuff. So yeah, we'll be playing with tensors a lot in this video, and we'll be seeing how we do that, because tensors is very important if we want to move on to the next step of like training deep learning models, right? Because that's where tensors are going to be used primarily. So this is a pretty important video when it comes to understanding the basics and fundamentals of the inner workings of PyTorch. So extremely excited for this video. Let's get on with it. Finally, we're down to doing some experiments. I'm on my VS Code. As you can see on the right hand side, I have my PyTorch environment activated. This is a VS Code Jupyter extension actually, which brings your Jupyter notebook into VS Code. It's an awesome extension for people wanting to experiment with notebooks and scripts at the same time. Let's go ahead and do some experiments. So the first thing, we'll import our torch library, and along with that we will also import NumPy, since we will be testing out some interconvention between these two different data types. Let's create a tensor first. We'll go ahead and name our tensor as tensor1, and we'll create a tensor and pass a number 5 in it. We'll print the tensor, and as you can see, it's a tensor containing only one value, which is 5. If I print the data type, which is the D type of the tensor, you can see that it's torch int 64. So by default, PyTorch would create a tensor for you having values all set as int 64. You can also create tensors by passing a list of values. So as you can see, I'm creating tensor 2 over here and passing a list, and at the same time, if needed, we can also pass the data type, and we have the options of passing float 16, float 32. In this case, we're passing float 32, and let's go ahead and print the tensor 2 just like we did previously, but as you can see, these are all float values, unlike the previous tensor 1, which had an int value in it. We can also check the shape of the tensor. It's pretty easy. We can just call a tensor2.shape on it, and it will print the shape of the tensor. So there are two commands actually. There's shape and there's size. So both the commands can be used interchangeably. Shape seems to be an attribute in this case. It returns the torch.size, but the size function call, it's invocable. It's kind of a callable, so you actually have to suffix tensor dot size with 2 brackets. So that's how it works. So here I'm calling tensor2.size. As you can see, size is actually a callable. It needs to be invoked as a function, so size needs to be followed with 2 brackets as shown. Now we can also create tensors from NumPy values actually. This is an awesome feature. We can define a NumPy array just like we did in N1. So N1 over here is a NumPy array, and we have 1, 2, 3, 4, 5 defined. In order to convert this into a tensor which is usable by PyTorch for any kind of operations, the only thing that we need to do is call torch.fromNumPy, and automatically the NumPy array, which was N1, is converted to the tensor and T1 from N1, and the data type is also preserved actually. That's the best part. We can also create tensors from random numbers. So the functions available are randint, random. So randint expects a lower integer and a higher integer bound. So for example, here I'm passing 1, 10. So the lowest random number will be 10, and the lowest number would be 1, and the highest would be 10. And I've specified the size as well, which is 2, 3. So there you go. We have a tensor of shape 2, 3 from random numbers completely. And now we're going to look at two very important operations that we can perform. It's squeeze and unsqueeze, which have been actually borrowed from maybe MATLAB, and it's present in NumPy also. The basic idea is if you have a multi-dimensional array or a tensor, squeeze actually allows you to remove a particular axis of depth 1 or n plus 1 per se, and unsqueeze just does the opposite. It will actually add another axis of depth 1. So the way of indexing a particular value just changes. That's what happens. So here you can see that I have a tensor called T1 with a lot of axes, and what I'm trying to do is I'm trying to add another axis of shape 1 at the third position. So you can see that I had 1 2 1 4, and that was the dimension. Now we have 1 2 1 1 4. Now let's check an example of what happens if we try to squeeze it, right? So here I'm creating another tensor by calling torch.squeeze, and I am passing T2 as an input, which was the unsqueezed tensor, and I'm passing third index. So now you'll see that the two axis 1 1 has actually become 1. So we have removed one axis. So that's how it works, guys. So the next function that we're looking at is the mean function, and it's pretty prevalent and used for most of the EDA activities. I mean, you wouldn't be able to do without the mean function, right? In order to demonstrate that, I would be taking a tensor T4. I would consider a multidimensional tensor, and we'll be using the rand90 function to generate it. The numbers in the tensor would be between 1 and 20, and we'll have a 4x3 shaped tensor. The data type for this would be float 16, and as soon as I create it, we'll have T4, which is a 4x3 tensor, and there will be 12 values in the range 1, 1, 20. So this is the 4x3 tensor that we have. And now in order to calculate the mean, we'll be using the torch.mean function. Now the mean can be calculated in two ways. We can either calculate the mean for the 0th axis or the first axis. So we can either do it horizontally or vertically if you want to visualize in that way. So I would go ahead and pass 0, and as you can see, it has summed up in this tensor in the vertical way. So we have, if we go ahead and calculate the values, you'll see that 6 plus 4, that's 10, and then there's 17 and 13, so that's 20. So 20 plus 10, and that's 30, right? So 30 divided by 4, and you have 30 divided by 3, and you have what kind of a fuck all calculation is that? Wait a second. The next operation that we're looking at is a very significant and widely used operation, which is the mean operation, right? It's used for a lot of EDA activities. In order to demonstrate that, we will be creating a tensor T4, and this tensor is going to be a 4x3 shaped tensor, and I would be using the rand90 function in order to generate it. So here you can see I pass 1, 20, which is the minimum, the maximum values. The numbers can be or range between, and the D type over here is float 16. That's what I'm choosing it to be. So now as soon as I hit enter, we'll have a tensor of shape 4x3, and the numbers in the tensor would range between 1 and 20, and all of them are float 16, right? Now in order to calculate the mean, we can simply go ahead and call the torch.mean function. This function takes the dimension or the axis parameter as well, so either you can calculate it horizontally or vertically, if visualized in that sense. It's row or column. That's another term that can be considered. So I'll go ahead and pass 0 over here, and you will see how the calculation is playing out to be. So the first number over here you can see is 10, right? It has calculated it, like if you visualize it, it's calculated it in the vertical sense. If you add up the numbers, you get 6 plus 4, that's 10, and then there's 13 plus 17, that's 30, 30 plus 10, that's 40, and if you divide it by 4, which is the 4 rows that we have, or the 4 individual tensors that we have, that's 10, right? And then if you do it for the second column, then you have 18 plus 2, 20, then 29, and then 13 or 31. So if you divide 31 by 4, you get a 7.75, and that's precisely the number that we have. Now we can do it in the other way also. I'll just go ahead and change the 0 to 1, and now you'll be able to see that the calculation has changed a bit. you will see that the calculation has changed from 10 to 10.3359, because now the division is actually happening in the horizontal sense. So if you add up 18 plus 4 and 9, you get 31, and you divide that by 3, you get a 10.33. So that's how it's working. So the next operation we are looking at is the summation or addition operation. Just like the mean, the summation can also be done in a row or column wise. So we choose the same tensor as before, generated using rand_int, and now I'm calling the summation or sum function over the T4 tensor. So we just create another tensor called T6, and now you can see that it has been summed up. So choosing 0 will sum up in the columnar way, just like it did previously, right? So if you look at the numbers, so if you add them up, you'll see that 15 plus 7, that's 22, 22 plus 2, that's 24, 24 plus 9, that's 33. And then if you look at the number below, you will see that it's 33, right? So that's how the summation works. Cool. So the next operation that we're looking at is the standard deviation operation. The invocation is very similar to the mean, just how we used torch.mean, right? You just have to call torch.std, and you call it over the tensor of which you want the std to be calculated, and you also have to pass the dimension or the axis, just like in the previous example. So you pass either 0 or 1, and then based on that your std would be calculated. So the next operation that we're looking at is a very interesting operation. It's called the split operation, which allows you to break down your tensors into chunks, right? You can break them down to smaller tensors of different shapes. So now, in order to demonstrate this, we have T9, which is again a tensor of integers from 1 to 30 and is of shape 3 cross 4. Now we can simply pass this tensor to the torch.split function. We pass T9 over here and we specify the length as 1. Now what it does is it divides the tensor by 1. So that's essentially what it has done, right? So since it was 3 cross 4, now we have 3 tensors of shape 1 cross 4 each. So there's like 3 individual tensors. That's what's happened. Now since we have divided by 2, so it has chunked it. So there are chunks of shape 2, right, along that dimension. So it's like 2 cross 4. So that's the first tensor that we have. But the last value, since it was not divisible by 4, so it is kept as it is. If you look at another example, so over here it's very interesting because the initial tensor was of shape 3 cross 4, right? So we essentially had like 3 rows and 4 columns. Now when I tried to divide it or chunk it into groups of 3 again, it was not possible because it was already one single tensor of shape 3. So that's the only tensor that I have, which will essentially have a shape 3 along that dimension. So here by default the dimension is 0, right? So even for the first case when we passed the value as 1, so it was actually broken down along that dimension, which is dimension 0. So since along dimension 0 there are 3 values, like 3 is the axis, like on the axis the value is 3. So it's like 3 was divided into tensors of shape 1 cross 4. So essentially if you take 3 and you equally divide 3, so you will have 1 cross 4, right? So you'll have 1 and then 1 and then 1 again. Now you have 3 and you want to equally divide it into groups of 2. So the first 2 tensors along that shape are taken, and you have the first group. I'm talking about the second example, by the way. So the first group, which is a tensor of shape 2 cross 4, but then the last row along that axis is left out because there is nothing to club it with. In case this was a tensor of shape 4 cross 4, then you would have seen 2 tensors of shape 2 cross 4 each, right? For the second example. So if it was T9, 2, and there was essentially a tensor of shape 4 cross 4 instead of 3 cross 4, then calling a torch.split would have equally broken it down into 2 chunks of shape 2 cross 4 each. So that's pretty much how it works. So essentially along that particular dimension, so dimension 0, so along that, if we pass dimension 0, so along that dimension to split it. If I pass dimension 1, along that particular dimension to split it. That's pretty much how it works. So the final operation that we're looking at the stack and the concat operations. These are very essential operations. Concat is used all over the place, like for a lot of concatenation operations where you have multiple outputs coming out from different neural networks or different models, and you want to concatenate them. So that's where concat, the cat function, is used. So here we have two tensors of shape 1 cross 3 each. Now if I go ahead and concatenate them, right, so what happens if I press T3? So you can see that it is a new tensor, and along the same axis, along the same dimension, the two tensors are added up. So a new dimension is not created. So the first tensor was of shape 3, right? So the length was 3. The second tensor was of length 3 again. And when I call a torch.cat, it adds it up along the same direction, same axis or the same dimension. So T3 now has a length of 6. So there you go. When I print T3.shape, it shows us that the size is 6, right? Now let's go ahead and try to stack them up. So what happens when we stack them? So stack actually, oops, I made a mistake here. I am actually supposed to pass a tuple of tensors. There you go. So now, yep. So stack, what it does is stack actually adds a new dimension altogether. It does not add them up in the same dimension. So if I call T4.shape, you will actually see it's 2, 3. So there's like 1, 3, and then there's again another 1, 3. So it's like 2, 3. So if I do a T4.0, right? So T4.0 is actually a single tensor of shape 3. Again, like if I do a T4.1, right? It's again another tensor of shape 3. It's along a different direction altogether. So that's how stack differs from concatenate.